Hello, everyone. It's my pleasure today to introduce our very own Dr. Yue Hu, who joined the IAS as a NASA Harvard Fellow. And he received his bachelor degree from joint program at the Tonji University and University of Bologna in Italy. And then his PhD degree from University of Wisconsin-Madison, where he was working with Alex Lazarian on a variety of topics, mostly related to magnetized turbulence in the ISM and all the kinds of physics which is happening in there, including the turbulence structure, the turbulent dynamo, cosmic ray propagation, star formation, and so on and so on. He is using a variety of methods in his research, including the numerical simulations, the direct observations, and the data interpretation. And today he is going to tell us about 3D galactic magnetic field and its implication for CMB foreground polarization. Okay, so we take the lead.
Thank you very much. And thanks everyone for coming to my seminar. And today I'm going to talk about the 3D galactic magnetic field, and I wanted to relate it to also to some application to cosmological foreground polarization. So I might start with the very beginning, like from the Big Bang. And we know that from Big Bang, there's a theoretically expected very important epoch that's called inflation epoch. It's the inflation means that the size of the universe increased by maybe factor 10 to the power in a very short time. And such inflation epoch can produce a very strong background of primordial gravitational wave. So gravitational wave and the primordial gravitational at the outside can produce to sharp the same polarization signal. So if we have a polarization signal made from CMB background, we can decompose it into two components, E mode and B mode. E mode is almost produced by scalar field like density fluctuation, but B mode is only produced by primordial gravitational wave. Therefore, if we can detect the B mode from the CMB polarization signal, and it's a strong evidence of the primordial gravitational wave, and it's evidence of the inflation theorem. But the problem for detecting the B mode is galactic foreground. Here, that's a plot from Planck collaboration in 2015. The same B polarization signal is expected polarization signal is this line. It's highly overwhelmed by the synchrotron polarization at low frequency and dominated by the thermal dust polarization at high frequency. Therefore, if we want to detect the B mode, it's very difficult because the signal is highly contaminated by the synchrotron polarization or dust polarization from the galactic foreground. Therefore, it's very important, and if you wanted to it's very important to model the galactic foreground if we wanted to detect the B mode and we wanted to detect the primordial gravitational wave. So let's have a look what does the foreground look like. Here, I mean the dust polarization foreground at high frequency, maybe around 300 gigahertz. So here, that cartoon shows like maybe the shell is the expected same B polarization. And here that's the signal, the core is the signal from the Milky Way. So our satellite here is running in the central galaxy. So here we wanted to model this part to remove the foreground signal so we can detect the background CMB polarization. And the dust polarization is emitted by the thin dust. It's a surface of very large charged particles, and it's rotating perpendicular to the magnetic field. Because such a preferential rotation is polarization signal is perpendicular to the magnetic field. Therefore, we know if we know the polarization direction, we rotate by 90 degrees, we know the magnetic direction. That's a dust polarization. And the dust polarization and its correlation with magnetic field. And all mathematically speaking, here the dust polarization can be characterized by two parameters, Stokes parameter Q and U. And they are highly related to the magnetic field, like here X, Y, Z, and total magnetic field component. And then we can also further write it as a combination of the plane sky magnetic field angle and also the inclination angle of magnetic field. And the polarization intensity is given by the square root of Q square plus U square. Therefore, if we wanted to know to model the foreground dust position, we need the magnetic field information. So then magnetic information, especially we need the magnetic information of our galaxy.
Presumably the polarization also depends on what the dust actually is, not just the magnetic field. Is that just very well understood?
Oh yeah, it depends on the P0. P0 is intrinsic polarization fraction. It depends on dust polish. But for the diffuse media like the H1 large scale galaxies, it's well known this value can be more constrained from dust model. But if we are talking about star forming regions, it's more complicated. For our purpose, this factor can be well constrained. The more complicated one is magnetic field. So let's see if we wanted to know magnetic field. Currently, we already have like 4 methods. Typically, we have 4 methods, 4 approaches: dust polarization and synchrotron polarization, Zeeman splitting, far dilatation. They can probe the magnetic field in different phase ISM, different regions. Like for dust polarization, it can provide the magnetic field orientation of the Planck sky in the dust, in the star forming region or dusty ISM. But for synchrotron polarization, it can trace the magnetic field orientation only in the ionized cosmic ray field ISM. And the Zeeman splitting and far dilatation can not give us the Planck sky magnetic orientation, but only the strength of magnetic field along the line side. Therefore, the information actually is not enough, and it's the magnetic field we know it's a 3-dimensional vector. Here, each method can only give us either a 2D orientation or just the 2D alongside magnetic field strength. So it's not the information provided by the typical method, like the typical approaches cannot be used to fully model the galactic foreground or the polarizations or the foreground polarization. The first limitation of the typical method is it's an integrated measurement. For instance, for polarization, it's measuring all the signals starting from the Earth to maybe to the end of the living universe. So it contains also the signal from the foreground and also background. That's well known. So as the first step to model the galactic foreground or to model the galactic magnetic field is to get the 3D spatial distributions of the magnetic field, to decompose the magnetic field into different vectors and along the left side. And the second limitation we already mentioned is the typical method can only trace 2D magnetic field, either the Planck sky magnetic field or an angle or the magnetic field strength along the left side. So the information is not enough. What we need to do is to solve it. We need also to trace the 3D magnetic field, not just the Planck's angle, but also the inclination angle, the critical inclination angle of the magnetic field, and also the strength. With those information, 3D magnetic field and 3D spatial distribution, then we can have enough information to model the galactic foreground polarization. And the solution here we are thinking about is to use spectroscopic observation to get 3D magnetic field. Spectroscopic observation looks like this. Here is a spectroscopic cube, and it has X, Y, Z, and V component. Here, that's the third axis is the velocity, because we have the Doppler shift effect, so we can measure its velocity. So if we take a look, that's one also observational example of the H1 data. Here, X, Y, Z plane looks like this, and the Z axis is a spectral profile. That's how the spectroscopic data looks like. And importantly, the data can provide us the alongside velocity. So if we have velocity information, we can use galactic gravitational curve, then we can get the 3D spatial position in the Milky Way. So the key point is whether we can find the magnetic information just from the spectroscopic observation. And the best choice of the spectroscopic observation here we are thinking about is H1 emission, because H1 is well mixed with dust. So if we know the magnetic field associated with H1 is also the magnetic field associated with dust, and also as Nick also mentioned, like the dust properties for H1 diffuse gas is well constrained, unlike the star forming region is more complicated. So we choose to use H1 to trace the magnetic field. And here, that's if we wanted to use H1 to trace magnetic field, maybe I can also ask you a question. Here, that's one synthetic H1 map or H1 map, and whether you can find the magnetic field for just this image. And the answer is no, because it's a hydro simulation. It has no magnetic field. But what if we include magnetic field like image simulation? As you see, the H1 structures actually has been changed. It's elongating along the magnetic field direction. So even if we just look at the image, the structure's elongation direction, we already can know roughly the magnetic field is along the perpendicular, along the vertical direction. So that's that means also the H1 emission is correlated with magnetic field. But also maybe you may also want to ask, H1 is a neutral gas, it's a neutral flow. How can it feel magnetic field? Because it's not charged. So whether it can feel MHD or hydro effect, that's a question. But here we have to mention, instead of just the neutral hydrogen or neutral particles in the intense medium, we also have ionized charged particles. Charged particles can feel magnetic field, so therefore for charged particles, it's regulated by MHD effect. And importantly is a charged particle and the neutral particle can be well coupled via collision. If their collision is frequent enough, the magnetic field effect can be transferred from ionized charged particles to neutral particles. Therefore, even if it's a neutral flow or neutral particles, it can still feel the magnetic effect if they are well coupled. And the critical parameter here is, as I mentioned, is coupling is the collisional frequency. The collision between ions and neutrons should be frequent enough, otherwise the magnetic effect cannot be transferred. And here, if you plug in typical physical parameter like the gas density, the drag coefficient, and also alpha speed, you can get the decoupling scale, like at which scale they are coupled is around 0.1 parsec. Therefore, at the scale we're considering about the large scale magnetic field structure in our Milky Way, we can think like we can think about like ions and the neutrons are coupled. Therefore, even for neutrons, they can still feel the MHD effect. Here, that's also MHD two-fluid ice simulation. The top is ion density, and the bottom is the neutron density and the neutron velocity. As you can see, they are identical. Actually, the two, no matter whether it's ion or neutrons, they can both feel the magnetic field effect.
How do you know that scale? 0.01?
Oh, here you can take like the ion density. Here, that's here you should like this condition gives the frequency is larger than the k times the alpha speed. That's alpha waves frequency. So the critical scale is like you can equal these two scales, these two frequency.
But gamma D is a free parameter, no?
Gamma D is not a free parameter. It depends on the collision or the cross section of the particles. So it's also almost a constant value in ice and large scale ice.
But is that like, do you know that well?
Yeah.
Collision perception.
Yes, it can be done. And also the ion density, neutral mass density, the neutral mass density, you can get it from a neutral hydrogen observation. Ion density, proton H plus emission. So this parameter can be well known. So this scale can be well constructed. Maybe it has some like variations, but it's the order of the 0.1 parsec.
What is the simulation? Is it like with the guide field is you of 3D?
It's a 3D with 3D simulation, MHD turbulence simulation.
Yeah. With the guide field?
With guide field.
Which direction?
Towards the page.
Okay, so it's similar to the hydro central which you showed on the previous.
Yes. Because here I didn't update the figure. Otherwise, it's maybe it's better to use the guide field along as a vertical or horizontal. Yes. Here I didn't update the figure, so here it's the guide field is towards the
These neutral hydrogen surveys, are they 21 centimeter high?
yeah 21 centimeter.
Can I ask a quick question as well? In all regimes that you're interested in, is ideal MHD what you're using for these hydrosims?
Yes, ideal MHD without safe gravity without safe gravity, and the scale is larger than 1 parsec.
Okay.
Hydrogen. And in some cases also larger than 10 parsec because we don't consider molecular cloud. It's just atomic hydrogen.
Okay, thanks.
But here, okay, here we mentioned, okay, we can use near H1 neutral hydrogen to trace magnetic field based on its morphology. But actually, the density structure of H1 is not a good tracer of magnetic field. Here we can take several like observational example and numerical example here. That's magnetic field measured by the Planck polarization. We see in some case here the magnetic field or the density structure actually can be perpendicular to the magnetic field instead of parallel. Like also that might be more clear for you in the numerical simulation. It can in some case in some regions the density structure follows the magnetic field, but in some regions it's perpendicular to the field. So the density structure is not a very good tracer of magnetic field. A better tracer is the velocity, because here that's also a simulation effect as taken from MHD simulation. And even if, like you say, even if the density structures is perpendicular to the magnetic field, the velocity structures are still parallel to the magnetic field. Because for the velocity structure is less affected by the shock effect, the compression of magnetic field is not so significant. So velocity structure is a better tracer of magnetic field. So we want to actually trace the magnetic field using H1 velocity field. It's more difficult.
What velocity are you plotting there in the plane of this? What is the plot?
Here, that's a velocity amplitude.
Just the
Amplitude.
v square or the
Total. But even if you just take the long side velocity component, it's still anisotropic. It's still you should say such an elongation.
Slice, or this is like projections of all the velocities?
It's just a slice. It's not a projected. So we needed to understand why also velocity is better tracer of magnetic field. Yeah, I have to mention emission turbulence. Because besides magnetic field, turbulence is also a very fundamental and important factor in ISM. Like here, that's the power spectrum measured by different different method. Like here, there's rotation measure fluctuation, velocity fluctuation, alpha fluctuation. They all show that the fluctuations in the ISM follow a big power law that's expected from the Kolmogorov turbulence. And also, even if we look at the small scale young stellar object and we calculate the velocity fluctuation, it also roughly follows the expected of the Lasson's law at the scale larger than 10 parsec. So we know that the magnetic field of the turbulence is fundamental pervasive in the ISM, and we want to understand its property and why the velocity structures are preferentially perpendicular parallel to the magnetic field. So we can think about emission turbulence because we have magnetic effect. Therefore, the turbulence can be described as anisotropic velocity eddies. Just think about we have two eddies and they are moving along the opposite direction. And the time to destroy the parallel scale equals to the time to destroy the perpendicular scale. So that's L parallel divided by alpha speed. It's equals to the L perpendicular to divided by the turbulent velocity. So such critical balance, if we combine with Kolmogorov law and the turbulent velocity is proportional to the scale to the 1/1/3, we have such correlation that suggests the turbulent eddy is anisotropic. The parallel scale is much larger than the perpendicular scale. Like here also showing the MHD turbulent simulations. We take a structure and here the background segment is magnetic field. The parallel scale is much larger than the perpendicular scale. So that explains why the velocity structures is preferentially parallel to the magnetic field because the magnetic field effect and also the turbulence effect. So right now we know the velocity structure are preferentially parallel to the magnetic field. So if we can detect the elongation direction structure, then we can know the magnetic direction. That's very simple. So here in observation, we try to detect the detector of the elongation. We use this gradient. Because here we know here the parallel scale is much larger than the perpendicular scale. So if we calculate the gradient of the velocity field, we find is dominated by the perpendicular component. Therefore, if we know the velocity gradient direction and rotated by 90 degrees, we know the magnetic direction. Here the gradient is just like a detector of the anisotropy, the detector of the elongation direction. So that's also what we expected. And here another question is, where is the velocity information in observation? In observation, we're measuring the brightness, we're measuring the intensity. How can we detect? How can we get a 2D map of velocity and calculate the velocity gradient? So we have to go back to the statistical properties of spectroscopic observation. As I mentioned in the beginning, I think some of my slides, the spectroscopic observation means the intensity of the cloud of the H1 emission is measured in XYZ space instead of XYZ space. So the third axis is velocity, not just the space. So that means that there is some velocity effect that can change the density distribution or the intensity distribution in real space. Like here, I give you a numerical experiment. Here, initially, I set up a constant density field and assign it with a turbulent velocity field, and then map this constant density field into velocity space. And we can see its shape is highly distorted and due to its velocity effect, because here the third axis is velocity, not z. And then we take one thin slice. If we take a slice at one velocity, we see there are some structures. But actually, initially, it's just a constant density field, so there's no any structures. Those structures are purely created by velocity effect. So we can see actually we can get the velocity information from the observation because of the nonlinear mapping from the real space to the velocity space can involve velocity, and such velocity effect can create the anisotropic intensity structures in the spectroscopic slice or spectroscopic channel. Here is another example to better illustrate this effect. Again, here initially I use a constant density cube, but still use a turbulent velocity cube. And I use the two cubes to create a synthetic spectroscopic line. And let's see what will happen. Here, initially the red, okay, here that's initially the red shadow area means the integration range for the intensity along the velocity axis. So if we integrate it from where the minimum velocity to the maximum velocity, everything is raised out because initially it's a constant density cube, so it's just constant density map. But what if we decrease the integration range of the velocity channel? We can see here some structure appears, because here if the channel width, the delta V is small, the velocity effect is more significant. So essentially, if the velocity channel width is smaller than the turbulent velocity dispersion within this dashed lines, the channel map is purely, you can see there are many structures in the channel map, and those structures are only created by velocity effect. Therefore, we can use actually the thin velocity channel, just take a slice of the spectroscopic data, and the velocity width shouldn't be larger than the turbulent velocity dispersion, then we can get the velocity information.
So I have a maybe naive question. So what are the physical sizes that are involved here? They're like parsec scales or greater than parsec scales?
Yes, parsec scale.
How much, what are the like dynamical timescales associated with this? Because in principle, you could do some sort of temporal correlation in addition to this, because I mean, so you're showing things where you start with a constant density cube, but in reality, you could have more complicated structures. So I'm wondering if you could, say, okay, well, I know that I'm gonna see stuff that happened 1 parsec behind the other stuff, I'm gonna see it some number of years later or whatever. Can people do temporal correlations like that?
Temporal, I don't think I don't think we can do temporal correlation right now for the regime in our mind. It's maybe roughly around 1 million years. So the time scale is very, very large. We cannot do that. So we can only do the spatial correlation on this map.
These simulations are all incompressible then.
It's compressible.
It is compressible.
It's
So you only initialize with uniform density.
Yeah, uniform density,
Okay.
but the velocity field is compressible MHD. And without safe gravity, still we are looking at the atomic hydrogen.
We already had some compressions. So in this video, we might see some later stage of evolution, the turbulence. We had some compression, the density here was constant for this week.
For this video, that's discussed, but if you include the real density, it has compression. So here I just wanted to make a clear experiment without the density effect. Of course, in reality, in real observation, there is some real density structures. But everything depends on whether, like this, I think where everything depends on the channel width, whether the width is small, narrow enough. If it's narrow enough, the density structure also can be separated into different channels, and the velocity benefit is significant. But if we have very, very wide the velocity range, then it's only the density effect. So it depends on the width, the integration range of the channel width. If you
That's a statement about the scale that you expect the structures.
the scale.
Yeah.
Physical scale, you mean like here the scale created by the velocity effect?
No, and the real structure.
Oh, the real structure, yes, the real structure. It's
There's some relation between the frequency, the channel that you need, velocity versus the structure, like the physical structure.
yes, there's some correlation. I don't remember its correlation, but like here in this paper, that's my supervisor Lazarus paper like 20 years ago. They formulated the correlation between density and the velocity. So there's some correlation between you can separate them.
This is also a naive question, but like, how is the mapping in this case between like the z-axis and the velocity axis that you observe? Because like, I guess if I'm thinking in cosmology, the standard example for you to convert a peculiar velocity to a shift in the density along the line of sight, you basically need a time scale to convert the velocity into a distance. And so the Hubble constant is what ends up showing up there. It's like a peculiar velocity relative to the expansion rate of the universe. What's that sort of time scale here for you to get a conversion to?
The time scale of the velocity here is in what the velocity let me think about. Because the mapping of the velocity comes from the Maxwellian distribution. Like here, if like think about we have total velocity, let's say the total velocity, and we minus its turbulent velocity. Maybe we also need to consider also the galactic rotation shear velocity. And what is left is almost the sum of speeds. So the density distribution in the density distribution in space is like it's a Maxwellian distribution. So I don't remember the exact form, but it's something like phi, something like that correlated with velocity, somewhat velocity. So I think here the time scale is very, very short. So it's more like the thermal, the order of thermal density scale. It's because this is what we get as a distribution from the Maxwellian distribution. So we don't need to consider about how to consider this.
Yes, I imagine the Hubble constant here doesn't play a role, but I was just wondering.
What is the relation between the frequency and the distance given by the rotational curve?
Yes, there is some correlation.
So that's basically formula is, I mean, if you neglect the width of the line, it's just velocity, it gives you the distance to the where in the rotational curve hydrogen has that frequency.
Here, when you like here and in here, like for the distribution, maybe for just one H1 cloud, that's simple. Here, that's one cloud is Gaussian distribution.
Then you spread by.
Yes, yeah. This peak velocity here, maybe with zero, that's correlated with the galactic gravitational speed. But this width, this dispersion, that's caused by the turbulence. That's the problem.
But you use that width at all and mapping between?
Yeah, in the mapping, we can take here. We are not just take this with zero here. That is. V.
So the channels that you use are smaller than small channels.
Yeah.
As you move through many channels, is the V0 effect there?
Yes, here maybe we can use this one. We can also use this one. We can also use this one. That's all.
Do you use the actual shape of the distribution? So like, do you expect there to be correlations between one channel and the next channel? Like you require that whatever's going on in reality follows this Maxwellian distribution, and then you use that to say, okay, I see something in this channel, and therefore that implies that in the next channel I should see something else. And you deconvolve it all that way?
We can get the correlation statistically. Yeah, there should be some correlation statistically because here is whether some intensity is distributed to this channel or to this channel. It depends on the velocity, and velocity depends on the turbulent field and turbulent field maybe scale. So I think there's some correlation statistically, maybe like power spectrum, we can see some correlation. But if you just saying about the structure, morphology of structure, maybe it's not so important. We can only say there are some statistical correlations.
If you were to do some kind of fit, for example, so you have the observation, and then you want to fit that mapping from Z to do you then fit the thermal? Do you fit the temperature as a function of location in the bulk as well?
Temperature as
Because the temperature gives you your sigma V in some sense.
in observation, we don't need to fit it because in observation it's what we measured is what we measured. Here this one. This is the spectrum we measured from observation. It's directly there. We don't need to do any assumption.
But in principle, that spectrum could be, in a very simple case, right? You have a sheet of gas with one temperature, and you have another sheet of gas with another temperature, and you're looking this way. And so you see this, and there are different locations.
Yeah, different.
So you see this produces some distribution, and then this produces some other distribution. You see the set of those. And in principle, this one could be very hot, and this one could be very cold, and so this one, right? And so if you just see a single spectrum, and then you want to fit the overall three-dimensional structure, then presumably you need to also constrain the velocity of the different, or the temperatures of the different components along the line. Or does that not matter? I mean, it's possible that these are just very, very.
It doesn't matter here because yes, it's correct if it's there are different temperatures like one hot and one cold, then can be combined into just one velocity effect. But here, whether it's like hot media or warm media or cold neutral media, they are all correlated with, like at the scale we are considering about, they are correlated with turbulence. So the warm media is anisotropic, and the cold media is also anisotropic. Even if they combine together, they are also anisotropic. Maybe the temperature can have some effect to change the expected, maybe like the ratio between the parallel axis to the perpendicular axis, but the elongation direction does not change much. Maybe in some sense, like the statistical, they can shift it a little bit because temperature difference. But here, I don't think it can change our purpose to trace magnetic field with this structure. Okay, so here, okay, right now, how can we trace magnetic field again in observation? Here's the first thing observation, we have H1 cube, and we take one velocity slice, and then we calculate the gradient for each pixel, and take a subregion and fit it with Gaussian, maybe Gaussian, and also histogram. The peak value will give us the magnetic field direction. And here that's also a numerical example. Here the red segment is gradient and blue segment is polarization. And this averaging over subfield is also critical because turbulence properties is always a statistical concept. We cannot say for each individual pixel it has some correlation with magnetic field. We can only get the correlation when the sample is sufficient. And now, okay, we can calculate the gradient orientation for each velocity, each side velocity, and we get the gradient direction. And we know H1 intensity, and we can get the intensity and H1 intensity, and we assume it's proportional to the dust density. Then we can construct the pseudo-Stokes parameter, and to predict the magnetic field orientation of the Planck sky. Here, that's at the top, that's magnetic field predicted from H1 and using the gradient method. And the real polarization, dust polarization, is characterized by the Stokes parameter. And here, that's a comparison with the Planck dust polarization at 353 GHz. And you see they have very good agreement. But here, of course, you can see here the information is still not enough. Right now, we have the Planck sky magnetic field orientation, but what is missing? Magnetic field inclination angle. So if we want to fully model the polarization, we still need to find the information gamma.
How did you get the NH1 as a function of V?
H1, because here, H1,
Same observations.
the observation here, that's observation here, that's what we measured as
So it's just some combination of
It's a
the
combination.
intensity and its gradient. that you
yes,
use.
yes, it's a gradient of some H1 intensity, but my point is such an intensity structure is created by velocity effect, dominated by velocity effect. There should be also some density effect, but dominated velocity effect is important.
Can I ask a question? Just because this comment that you made, so like all the examples you've shown is a constant density and then some velocity distribution and the resulting effects. But presumably if you have very extreme density fluctuations, is there sort of a balancing act of, what is the variance of the density fluctuations relative to the sort of scalar variance of the velocity fluctuations at which the observed map is dominated by one or the other?
Yeah, it could be actually here because right now, yes, there should be some density fluctuation. It could be important, and especially for shock effect. Density fluctuation for significant shock effect. But here, the first point here is for H1, its temperature is not so low, like molecular is 10 Kelvin. For H1, even if it's cold neutral medium, it's around 100 Kelvin. So the sun speed is a little bit higher. Like even for H1, it also has warm medium and also unstable medium. The temperature can be 1,000 and 1,000 and 1,000. So compared to the typical sound speed to the turbulent velocities, it's typically subsonic or transonic. The supersonic case is very different. So the shock effect or density fluctuation is not so significant in the H1 cloud. And the significant density factor happens in molecular cloud. The temperature is level 10 Kelvin, sun speed is very small, so that is highly supersonic. In that case, we need to further narrow the velocity range, because if its density is compressed by some Kelvin compression, its density should maybe. But if our density velocity resolution is high enough, it can still separate the density structure. So here, yeah, the whether it's dominated by density or velocity depends on the ways, still different ways.
But you basically need some sort of compression from a shock to have a density fluctuation large enough that it would dominate the final map. That's what you're saying. But we don't expect that the density distribution in the Milky Way is high enough. You know, the fluctuations are relatively small relative to the average. So they don't really
Here, if its density fluctuation is not induced by shock, it's not very high enough, then it's still not dominate, because if it's not shock, density fluctuation is also induced by the turbulent velocity fluctuations. Or energy injection is only for velocity, and we're not considering certain parameters. So if the energy injection is only to velocity, density fluctuation is also induced by velocity. So if without shock, density fluctuation statistically is also for the velocity statistics. So here I'm saying if it has shocks, the density fluctuation may not follow the turbulent velocity, and we need to be careful about that. And that happens in the cold neutral medium or the molecular cloud.
Turbulence type, you consider some compressible fluid problems preservations. That's why the propagating is both and which you want to consider.
Oh, because it's yes, because it's compressible turbulence. It's not just Arthon wave. Arthon wave is incompressible. For compressible turbulence, it has a slow mode and faster mode. They can compress the density field. Okay, so here that's an example of the comparison between the integrated magnetic field with Planck polarization. But here, as mentioned, we wanted to trace 3D magnetic field. So here also we made a comparison with starlight polarization, because for starlight polarization, we can know the distance of the star, and then we know where the signal is from, and we know the magnetic field orientation. So we are targeting at two clouds, one the intermediate velocity cloud and one lowest velocity cloud. They have different distance from the Earth. And here the yellow segment, which is magnetic field, and it had very good correspondence with the magnetic field traced by H1 and with the gradient method.
The temperature is different, so the roots of the Gaussian.
Yeah, it could be different. Yeah. With the Gaussian, it's different. So here we can separate from this peak velocity, to separate the two clouds. So here, as I mentioned at the beginning, the solution here to get 3D distribution of the magnetic field is using H1 and also combining with the Galactic rotational curve. Here is just one example of the 3D magnetic distribution along the direction cloud, and we get the distance information from Galactic rotational curve, and we achieve to get the 3D model of magnetic field orientation. Okay, so what we have done now, we use Doppler shifted observation H1 to get magnetic orientation, and we use Galactic rotational curve to find the 3D spatial position in the Milky Way. But that's not enough, because here right now all we have is just only orientation. We also wanted to know the strength of magnetic field. So the next step is to measure magnetic strength, also from the spectroscopic observation. So typically, how to measure magnetic strength in the ice and in Milky Way, we rely on the change of cycle Fermi method. It's proposed that the fluctuation in magnetic field, so essentially we have mean magnetic field, it has a fluctuation at the dashed line. The fluctuation is due to the turbulent motion. Therefore, if we see the magnetic field angle is like to distorted or the changed by some degrees delta theta, it's due to turbulent effect. That's a basic assumption of this method. So within this method, within this assumption, at the equilibrium state, the kinetic energy of turbulence equals to the magnetic field energy. Also, I mean the fluctuation of magnetic energy. And if we combine in the definition of alpha Mach number, it's the ratio between the magnetic fluctuation over mean field and the sonic Mach number is the turbulent velocity over the sound speed. We can get such an expression. The magnetic field strength is determined by the sonic Mach number, alpha Mach number, sound speed, and the density. For density and the sonic sound speed is easy to get in observation. But here the sonic Mach number and alpha Mach number are more difficult. So here our purpose, and we want to actually observation, we can get the sonic Mach number and alpha Mach number and combine them together, then we get magnetic strength. Here we still rely on the velocity as gradient, also using the H1 spectroscopic channel. Because theoretically speaking, if we have a strong magnetic field, a small alpha Mach number, and the structure is more compressed, and here is a narrow straight stripe, and the gradient orientation is preferentially only along one direction of a very narrow range. But if we have large alpha Mach number, that means magnetic field is weak, so it's more isotropic, and the gradient orientation can be to everywhere, any direction, and its distribution is more wide, is wider. And if we calculate such distribution by the top to bottom ratio, like the maximum value over the minimum value, we can get such a correlation between the alpha number and the distribution of gradient orientation. And this orientation can this correlation can be used to measure the alpha Mach number. And another parameter is the sonic Mach number. And the sonic Mach number we rely on the PDF or column density. Because as also Nika asked this question, if we have very highly supersonic case, the density fluctuation is very significant, and so its distribution is wide. But if we have transonic MAC is small, so density fluctuation is minimal. It's not so significant. So there is such a correlation between the dispersion of the column density PDF and also the sonic Mach number. So rely on the PDF for column density, we can also get the sonic Mach number. So you apply the two methods, the gradient orientation histogram, gradient orientation histogram, and also the column density histogram, we can use such the correlation with that correlation with sonic Mach number, alpha number, to get the distribution. Also using the H1 spectroscopic data and combine them together. And also we need to assume temperature and also to find the mass density of H1. Then we can get the magnetic strength and also the magnetic orientation, like also magnetic orientation only using the H1 observation. And we combine it with galactic curve, we get the 3D distribution of galactic magnetic field orientation and also galactic magnetic field strength.
How do you know the alpha Mach number there?
Alpha Mach number.
That's the V over VA, so the
Yeah.
VA depends on V also, right? So I mean
It's actually TB ratio here is a measurement of the dispersion of the histogram. We have a H1 map, and then we calculate the gradient, and we plot the histogram of gradient angle. If it's just a very highly filamentary structures, the gradient orientation is only at the left or right, so it's very narrow distribution. But if its magnetic field is weak, it's like isotropic, hydrodynamic, or maybe like hydrodynamic isotropic case, the gradient direction can be everywhere. So the distribution is wide. So the TB ratio is a function of the alpha number. So that's what we get. How we get the alpha number.
how do you calibrate that? How do you?
You mean observation?
Yeah, I mean, you have to know for which angular gradient, like for a given angular gradient, what is the alpha number? I mean, I can see that there is a correlation.
Yes.
What is the value of MA? How would you know that?
Yeah, we can plot the histogram, we can get the the value of t, right? The maximum. The maximum, that's the distribution function, the maximum, and we can get the minimum t. So that's what we can get in observation. We can calculate the gradient, we can plot the histogram. So TB ratio can be understanding of the. We take a subregion and also to plot. Maybe this is here. We take one slice and calculate the gradient for each pixel and divide the map into different subfield. And for this subfield, we can plot the histogram. And here that's a T, here that's a T, and we can get the T ratio. And then we can get the upper number. Okay, so I think we have talked a lot about the magnetic rotation, magnetic strength, but up to now, everything is just 2D. Okay. That's the final part. Yes. We wanted to have a 3D magnetic field. So 3D means it's a 3D vector, so it has a plane sky rotation. And the critical value is actually the inclination angle gamma. Because if we know the plane sky magnetic strength, we know plane sky magnetic rotation, we know the plane inclination angle, we can get with some mathematical algebra operation, and we do some algebra, and we can get the easy covenant basic. So the very crucial parameter here is the inclination angle. So the last part, I'm going to talk about how to get it. Again, let's go back to this plot. We know here the structure is elongating along the magnetic direction. So the plane sky elongation gives us the plane sky magnetic orientation angle. But the information provided for such structure is not just that, not just the elongation direction. We can also calculate the aspect ratio that for instance, the over the alpha particular. Such a ratio can provide the information about the inclination angle and also strength. Why is that? Because the elongation phenomenon is not a 2D phenomenon, it's a 3D. So what we observed, the elongation, what we observe is projected. So actually the elongation happens in 3D along the 3D magnetic field, and the projection due to the inclination angle magnetic field can change the aspect ratio we observed. Therefore, the aspect ratio is well correlated with the inclination angle. And also it's also correlated with strength, because we are thinking about in my weak magnetic hydrodynamical case, there's no such elongating filamentary structure, it's just isotropic case, and the ratio equals to 1. So this aspect ratio, observed aspect ratio, is determined by the inclination angle and the strength. This can give us information about the two. But of course, we have one parameter, but we want to derive two variables. That's not sufficient enough. It has degeneracy. So we have to think about another parameter. It's the curvature of the magnetic field. If we have strong magnetic field, it's just basically a straight line. Theoretically, it's a straight line, and the structure is elongating straight line in a straight way. But if we have weak magnetic field, the magnetic field can be easily bent. It becomes a curved line, and the curvature increases. So the curvature of the magnetic field is correlated to the strength. And of course, everything we observed is just on the 2D plane, so we need to also project it into the 2D plane. So the curvature is also influenced by, affected by the inclination angle. So here we have two parameters, the aspect ratio, we have curvature, and the two can use it to constrain the inclination angle and also strength the magnetic field. So essentially, let's make a summary here. We have the H1 spectroscopic map. We have the information about the plane sky elongation of structure. We have the aspect ratio of structure and also the curvature. And they have correlation with the 3D magnetic field parameters. But it's very difficult to find the correlation in analytical and also in observation. So here I choose to use machine learning. To use machine learning to do this job is much easier, and you can do it as well. Here is just our very simple machine learning model, convolutional neural network, and here is just three-layer very simple model. And the input is synthetic spectroscopic data from the network simulation, and it did the feature extraction and can give the prediction. I will not spend too much time on this. Here, that's a numerical comparison of 3D magnetic field predicted by the machine learning convolutional neural network CNN. And here, that's actual magnetic field in the simulation. Here, the top is sub-harmonic and the bottom is super-harmonic case. And we see that actually the machine learning can recover the 3D magnetic field very well. And in observation, I also try to apply this machine learning method to a molecular cloud. So here we make a comparison with Planck polarization. Planck can also give us a 2D magnetic field rotation. So actually, the machine learning approach can very well recover the plane sky magnetic field orientation. But here, the machine can do much better and can do more jobs than also just Planck polarization maps. And we can get the inclination angle. We can also get the alpha number. So here, that's a 3D magnetic field constructed for this cloud and using the machine learning method. So here, that's a summary. Here, what we have done yet, we get the 3D magnetic field distribution from the spectroscopic observation, and we can use machine learning approach to get a 3D magnetic field. And also, if we use the galactic rotational curve, we can get a 3D spatial distance. So essentially, we can get a 3D magnetic distribution in 3D spatial space, and that can help to fill in the gap in modeling the galactic foreground. Because right now we can actually to get the crucial inclination angle gamma, and then we can model the Stokes parameter to model the galactic foreground polarization. So that's all my talk. Thank you.
Yeah.
I guess you motivated this by CMB polarization. So if you take your observations and you produce this model, you subtract this from the Planck 353 gigahertz, how much is that? And how good is it? Because of course these correlations have some noise. So is it good enough? Does it reduce the polarization by 90%, 50%, 99%, whatever?
Yeah, that's what I propose for my faculty application.
Oh, you haven't yet.
I didn't do it yet because I don't know.
But you have this, look, you have something, you never took the difference.
Yeah, because that's orientation. That's just orientation. We wanted to, for same polarization, we wanted to know the intensity in the polarization. Here I didn't
Have
have
the Planck 353 test.
Yes, we can do that. Yes, we can. But I didn't do it yet. But I just think here right now, we have potentially we have approach to model the foreground polarization, maybe with consumption. And I'm not sure how well the result can be.
You maybe missed this at the beginning, but in your simulations, what is driving the magnetic turbulence? Are you just artificially driving it?
Artificially, the turbulence is turbulent box. So
Okay. Whereas in ISM, what is the most favored mechanism these days? Is it
solenoid driving. Wave number K is just a conventional method. It's not driven because right now we didn't like to use like for machine learning approach. We didn't use galaxy simulation. It's still we use a turbulence box to train the machine and take a patch of the sky to do the prediction. It's not the whole galaxy.
But in principle, the pipeline shouldn't be too sensitive to how you drive your turbulence or what instability is in fact leading to the turbulence.
I don't think it can affect much. I'm not sure actually. I don't think the mechanism. Because even if it's a solenoid driving, it can also produce a compressible functions. Maybe if you change it to compressible driving, the compressible component can increase. But right now, I'm not sure how much effect.
Okay, thank you.
Okay, probably we should stop here and do some other questions that sign up for one-to-one meetings. And also we have a few slots from dinner tonight. This is local.